Imagine this. The lights dim, the crowd around you erupts in cheers, and the first notes of your favorite song ring through the air. The excitement is contagious. You feel the bass dampening your chest, the energy of hundreds of people around you, all sharing this one unforgettable moment. You're standing shoulder to shoulder with friends, fully immersed in the experience of a live concert. An experience so simple, yet so profound. Now imagine that you couldn't stand. Imagine that the seemingly ordinary moment wasn't so simple after all. For millions of people with paraplegia, the ability to stand at a concert, to be on equal footing with others, is not a given. It's a dream. That's where our project begins. My name is Maaike Braquet, and I'm this year's team manager of Project March. For the last decade, Project March has devoted itself to improving the quality of life of people with a complete paraplegia. This is a medical condition characterized by the inability to voluntarily move the lower parts of the body, caused by damage to the spinal cord. There is no motor or sensory function below the level of injury, and therefore people with paraplegia are bound to a wheelchair. In the Netherlands, about 10 to 15,000 people have a spinal cord injury. Worldwide, this number adds up to 15 million people. Many wheelchair users are incredibly skilled at navigating daily life, and most public spaces in the Netherlands are wheelchair accessible. But still to this day, not all buildings are wheelchair friendly. And even if someone in a wheelchair can access a building, this does not automatically mean it's just as easy as walking the conventional route. Apart from these mobility issues, people in a wheelchair face other difficulties too, both physically and mentally. Being permanently wheelchair-bound decreases muscle and bone strength. The cardiovascular function deteriorates due to reduced blood flow in the paralyzed limbs, and bladder and bowel control are impaired. On top of these physical effects, sitting in a wheelchair can significantly impact mental health too. Imagine damaging your spinal cord, having to adapt to all the physical changes associated with that, and on top of that, being unable to maintain eye-level contact with the people around you. I think all of you can imagine the impact this has on your mental well-being. So, the ultimate question is, how can we help people with paraplegia, both physically and mentally? Our answer to this is with an exoskeleton. An exoskeleton is a robotic suit that enables people with paraplegia to stand up and walk again. This helps mitigate a lot of the negative physical effects of paraplegia. By standing up and applying force to the bones, bone density improves. Additionally, moving the paralyzed limbs enhances blood flow, which positively impacts cardiovascular health as well as bladder and bowel function. In the last 10 years, Project March has designed, developed, and tested a new exoskeleton every year. The 10 team of Project March consists of 27 students from various study backgrounds that passed their studies for a whole year to work together on the exoskeleton. We do this in close collaboration with our 28th and most important team member, our pilot, Daan van der Heijden. The pilot is the person that wears the exoskeleton built by our team. Daan is 32 years old and has a spinal cord injury from below his chest. After his first experience as pilot of the team of March 9, he is fully motivated to continue his position this year. And who better to tell you more about him than Daan himself?
Ik ben Daan van der Heijden, ik ben 32 jaar oud. Ik woon in Gaanderen, gemeente Doetinchem. Ik woon samen met mijn vriendin Tina en met mijn kindje Kira. Ik heb mijn dwarslesie opgelopen op 7 oktober 2017. Ik ging samen met een vriend meedoen aan een off-the-road rit. Helaas ben ik niet zo ver gekomen. Na de 3 kilometer ben ik gevallen. Ik ben in het zand gevallen en ik heb mijn rug gebroken. Ik heb waarschijnlijk een motor in mijn rug gekregen. Dus ondanks alle protectiemaatregelen die ik heb genomen, heb ik toch volledig mijn rug gebroken. De eerste keer lopen in een exoskelet, ja, dat was voor mij heel speciaal. Ik had natuurlijk net mijn dwarslesie gehad en ik heb het precies het jaar daarop, oktober 2018, met een exoskelet gelopen met familie erbij. Dus dat was heel bijzonder. Met Project March de eerste keer lopen, het blijft natuurlijk heel bijzonder om te zien dat het product wat ontworpen is door studenten, om de eerste keer te gaan staan, de eerste keer de stapjes te kunnen gaan zetten en dan ook daadwerkelijk meters te gaan maken of doelen te gaan halen. Dat blijft ook erg bijzonder. Ik voel natuurlijk vanaf een bepaald niveau voel ik niks meer, dus ik moet wel vertrouwen op het pak dat hij de beweging inzet. En de enige manier dat ik controle heb is met mijn armen en dus ook de krukken. En dat vraagt wel een bepaalde concentratie om erbij te blijven. En dan ga je de eerste keer staan en dan gaat dat heel rustig nog. En dan is het van oké, en we staan. Hartstikke mooi. En dan gaan we weer zitten. En dan was dat bijna de hele training. De volgende keer ga je dan al een stapje meteen zetten. En dan de keer daarop is meteen tempo weer hoger gezet. En dan gaat het alweer een stuk sneller. En uiteindelijk vertrouw je er gewoon blind op dat het gewoon goed gaat. Ik kijk zeker uit naar de trainingen. Ja, ik ben heel benieuwd hoe jullie exoskeleton gaat functioneren. Hoe het eruit gaat zien ook. Hoe het gaat fitten. En ja, weer de eerste keer staan en de eerste keer weer lopen is toch heel bijzonder. Kijk ernaar uit.
Now that you've gotten an insight into the person who will wear the exoskeleton, let me explain some more about the exo itself. The exoskeleton is designed with 4 main components, each inspired by the human body. First, we have the frame, which acts like our bones. It provides structure, supports weight, and keeps everything aligned. Next, we have the joints, comparable to our muscles and thus enabling movement. To control these movements, we rely on a computer, which functions as the brain of the exoskeleton. Just as our brains coordinate and control our actions, the computer makes sure that everything operates and moves seamlessly. Finally, there's a communication system. In the human body, nerves connect the brain to the muscles. In the exoskeleton, we use sensors and cables to perform this critical task, enabling communication between the computer and the joints. Together, these 4 main components create a system that mimics the human body in allowing controlled and natural movement. Enabling this movement for people with paraplegia has been the driving mission of Project March for the last decade. In these years, we have made incredible technological innovations. This year, we aim to take these innovations even further, not just to optimize the exoskeleton itself, but to amplify its social impact too. This year, we strive to make a difference that goes beyond technology. This year will be the year of Project March 10.
I'm sure all of you can't wait any longer to see the beautiful design of our exoskeleton. However, before we dive into this, I would like to take you on a journey through the developments that Project March has made over the years. My name is Luca van Beek and I am this year's Chief Engineer. Where do we begin? Project March started as a dream, building a fully self-made exoskeleton to enable people with paraplegia to stand up and walk again, to show the world what is possible when a group of young and dedicated students puts their minds to it. Now imagine having to develop such a complex system for the very first time, without the guidance of alumni. Project March 1 faced many technological and operational challenges, all while having to find a balance between innovation and the safety of their pilot. It's truly incredible what they were able to establish as a strong foundation. Let us take a look at the 8 designs that followed that made this dream a reality. So, what does an exoskeleton actually need to do? Similar to the suit of Iron Man, our exoskeleton combines strength, speed, and advanced technology into a robotic suit that, in our case, provides motorized movements for the legs of the pilot. For this, we started with the core functionalities, like sitting down, standing up, and walking. This is performed by flexion and extension in the hip and knee, a movement that is powered by the rotational joints, which have motors that spin and move 2 connected parts like a hinge. To achieve a more human-like walking pattern, more types of movements were needed. That's why the next Project March year designed an exoskeleton that enabled a motorized up and down movement of the foot. This movement is powered by the linear joints in the ankle, which have motors that also spin, but in contrast to the rotational joints, they create a push and pull motion, a motion that is essential for lifting the heel of your foot off the ground during a walking pattern identical to ours. Now we have movement in the hip, knee, and foot to move forward. But what about stepping sideways? a movement that is crucial for passing through narrow paths and avoiding people or obstacles. To achieve this movement, the same type of linear joint that is used in the ankle is now introduced in the hip. This means we can move our leg in an extra direction. To test how this technology can be used in daily life, the first 5 years of Project March were focused on the Cybathlon. The Cybathlon is a bionic competition where teams all over the world compete with their exoskeletons by overcoming certain obstacles that resemble challenges from daily life, like walking on a staircase or opening a door. After testing the core functionalities, there was room to innovate where there has not been innovated yet, by expanding the use of exoskeletons from inside to outside terrains. The next designs offered more freedom to the user. Achieving these functionalities asks for great innovations. That's why cameras were added, to be more aware of the surroundings and to create a walking pattern that was generated at the moment instead of pre-programmed gates. In addition, a prototype of pressure soles was implemented for detecting the ground underneath the feet of the exoskeleton. Apart from these earlier mentioned functionalities, there's one incredibly difficult feature that we want to achieve within Project March: balance. This is important because the pilot could have his hands free of crutches and use his hands, for example, to hold a drink or to hold the hand of their loved one. Project March 8 made the first steps in improving the balance of their exoskeleton by introducing torque and pressure sensors to all 8 of their joints. The following Project March year had the same goal as the first 5, winning the Cybathlon. To overcome the obstacles of the Cybathlon, Project March 9 focused on speed and reliability by designing the exoskeleton with the first self-made motor controller to increase the communication speed between computer and motors. On top of that, they designed an extra movement possibility in the ankle, allowing the foot not only to move up and down, but sideways as well. This is useful for walking on sloped surfaces or to keep balance. Even though we've come so far in the past 9 years, pushing the boundaries of exoskeleton technology, there's still room to push a lot more. The main goal of Project March is to give people with paraplegia the opportunities to engage in society on the same level as most of us. While previous years mostly focused on tackling the obstacles of the Cybathlon, we want to shift the focus of Project March even more to creating a social impact in our year. What is a better way to represent engaging in society than social events? To be able to stand on eye level again, having chats with your friends in crowded and vibrant environments. In these settings, balance and endurance from both the pilot and our system are topics of challenge. That's why we, Project March 10, will build an exoskeleton that enables the pilot to attend a standing concert by standing self-balanced while resisting external disturbances, and by walking more naturally to decrease physical effort by the end of July 2025. Let's take a look at the 2 main challenges of our team goal, starting with standing self-balanced without crutches. For you and me, maintaining balance is a thoughtless action, and you probably don't realize the underlying complexity. Let alone when you add in a crowd of people that move around you, causing the need for quick reactions to these movements. And of course, in crowded situations, you can't rule out that you might receive a small push from your surroundings. Movement around the exoskeleton or push from the crowd are examples of what we as engineers call disturbances. Remember this word very well, because you will hear it again later on. Let's take a look at the second main challenge of our team goal: decreasing physical effort. We have learned how demanding walking in the exoskeleton can be for a pilot. As one of them used to say, it's a new sport. The pilot now uses his hands, uses his crutches to keep himself balanced, which requires a lot of arm strength. By decreasing physical effort, we improve the overall comfort of using our exoskeleton. Attention that would normally be spent on focusing how to balance himself could now be spent focusing on his surroundings and enjoying the moment. We will explain the technical details of this problem and our solution to this later on. To overcome these challenges, we need both intelligent and creative solutions on software, mechanical, and electrical levels. By collaborating closely together, we have created a design that represents our immense teamwork and perseverance. To ensure that we have a complete exoskeleton with all its functionalities, we build on innovations from previous years and integrate those in our exoskeleton this year. At the end of the year, we will be able to stand self-balanced and stand in concert, and hereby get one step closer to achieving the vision of Project March, improving the quality of life for people with paraplegia. It might be a small step for Daan, but a big step for the many pilots that will follow. Now that you know what we want to achieve at the end of the year, let me show you exactly how we will make this happen. Watch closely to see our vision come to life. This is not just about achieving our goal. It's about pushing boundaries and conquering challenges, about making the impossible possible. We are extremely proud to show you the design of the exoskeleton of Project March 10.
Ik denk dat we nu al met het zelf balanceren en het vangen van stootjes natuurlijk alweer een mooie benchmark neerleggen. Het is natuurlijk niet alleen bij concerten bijvoorbeeld dat je een duwtje kan krijgen. Dat betekent ook dat je externe stoten van bijvoorbeeld bij het verzorgen van een kind stootjes kan opvangen. Dat is natuurlijk wel een hele andere mindset die je erin kan gooien. Maar dat betekent dus ook dat je staand bij kleine dingen toch als rolstoelgebonden ouder dingen kan doen met een kind die nu nog ver weg zijn. Er zijn ook dingen die ik meeneem daarin. Dus dat opent een hele andere deur die nu nog gesloten is.
Wow, thanks Siobhan for making this incredible video of our design. It's amazing to see what we're working towards and what could be possible in just 1 year. My name is Anneloes van Dijk and I'm the lead mechanical of Project March 10.
And my name is Rens Deur and I'm one of the software engineers of Project March 10. We are incredibly excited to show you the design of our new exoskeleton. And our team has been working tirelessly to make all of this possible. Anneloes and I will guide you through all the technological innovations that we're making this year.
As Luca mentioned earlier, our team goal includes maintaining stability despite disturbances, which can be, for example, a push from the side or back. When we experience a push from behind, our calf muscles naturally contract to pull our body back into balance. This pulling and pushing mechanism has been incorporated into our exoskeletons for several years now. It is achieved by a linear joint behind the foot. This joint accommodates a motor that actuates the movement, allowing it to replicate the up and down movement of the human foot during normal walking. This joint will also help the exoskeleton to remain balanced when exposed to disturbance from behind. However, if you consider disturbance from the side, for example, a push on the shoulder, this single linear joint is not sufficient to both stabilize the exoskeleton and down. A new degree of freedom was introduced in last year's design, the ankle inversion-eversion. This means that the ankle can now tilt sideways, which is essential for walking on uneven or sloped surfaces. Last year, this movement was actuated with springs, what we refer to as a passive joint, as it is not actuated by a motor. However, for our goal of withstanding side disturbances, a passive response is simply not enough. We need the exoskeleton to actively counteract the force from disturbances. To achieve this, we are introducing an additional linear joint at the ankle. But since space around the ankle is very limited, we had to come up with a compact yet efficient design. So rather than just adding another linear, we decided to create 2 linear joints that work together in a coordinated way, placed on the side of the foot. Here's how it works. For the up and down movement of the foot, one linear joint extends while the other retracts. This motion is required for normal walking and for regaining balance after a disturbance from behind. For the ankle inversion-eversion, both linear joints extend or retract at the same time. This synchronized movement creates the side-to-side tilting motion of the ankle, which is required for regaining balance after a side disturbance. With the 2 motorized linear joints at the ankle, we are now able to actively counteract the forces from disturbances, enhancing stability and control.
Having these 2 linear joints working together enables a level of control in the ankle that's never been achieved in a Project March exoskeleton before. We've essentially created a coupled system of 2 linear joints that work together to position the ankle however we like. But this coupled system also requires a lot more coordination from our software systems. And the reason why this is more difficult is not just that we have an extra joint, but the fact that they have to work together, as if they were a single joint. To bring the ankle to a new position, our software needs to steer these 2 joints at exactly the same time, with exactly the right speed and force. And in addition to this, we need to be careful not to place the ankle in an uncomfortable position for our pilot. And to ensure that our software takes all these factors into account, we precisely simulated the system to test its behavior and make sure that all the movements are smooth and safe. Through this simulation, we've made sure that our software understands all the capabilities and also all the limitations of this new ankle. And we can say with confidence that this new ankle will move smoothly and in a safe and comfortable way.
So, we've equipped the exoskeleton with motorized joints capable of responding to disturbances. But that alone isn't enough. To ensure precise control and stability, as Rens just highlighted, We also need sensors to provide continuous feedback. Imagine trying to stay balanced while someone gently pushes you. How does your body maintain stability in that split second? The answer lies in muscle spindles, specialized sensory organs within our muscles that measure changes in tension and stretch. When a muscle is stretched unexpectedly, these spindles send rapid signals to our nervous system, triggering the appropriate muscle to respond. For example, the calf muscles that contract when experiencing a push from behind. This continuous feedback loop helps us stay balanced, maintain posture, and move smoothly, even when unexpected forces come into play. In our exoskeleton, we are recreating this feedback system with a new custom-designed torque sensor. This sensor will be integrated into the rotational joint, which replicates the flexion and extension of the knee and hip. Just like muscle spindles detect changes and trigger a response, the torque sensor measures forces within the joint. These signals are then sent to the computer, which then adjusts the motor in the rotational joint to keep the exoskeleton balanced. By continuously sensing and reacting to these forces, we can maintain stability and enhance dance safety.
By adding these components to our exoskeleton, we've set the foundation to measure all the forces that are acting on our joints and to respond to them with full control over both our ankles. And with that, we can start thinking about the software that's needed to put these new sensors and joints to work. Once our exoskeleton is pushed, for example, on the shoulder or back, our software has a few milliseconds to decide how to react in order to keep the exoskeleton balanced. And this is quite a difficult decision to make, judging by the enormous amount of factors that we need to take into account. And to make this decision in such a short amount of time, we're deploying a model predictive control algorithm on our exoskeleton. And like the name suggests, this algorithm consists of 3 parts: a model, a prediction, and then a control output. And I will explain each of these parts one by one. For this algorithm to work, we start by creating an accurate software model of our exoskeleton. And this begins with a 3D model that contains every joint as well as the entire frame. Then we take all the sensor data that our systems produce and we bring it into this software model. And these sensors give us information about the current posture of our exoskeleton and how fast the different parts are moving. And we would like to match this software model to the real world as closely as possible. That's the model part of model predictive control out of the way. Let's continue to the next part, the prediction. We've created this whole 3D model of our exoskeleton. And now we would like to predict how it's going to behave in the future. What will happen if we power the motors in a certain way? And how do external forces like gravity affect the situation? We are going to run a full simulation that is able to take all these forces and movements into account. Because if we can accurately predict what our exoskeleton is going to do in the near future, then we will already know ahead of time whether it can stay in balance or that a correction may be needed. We can control and adjust how much power is going through the joints already before our exoskeleton starts to lose balance. And that brings us to the third and last part of model predictive control, the control action. In this part, we're going to decide how each of the joints should move such that our exoskeleton stays balanced. In other words, a control action is an instruction for each joint telling it how to move. An example of a control action could be that we move the left leg slightly sideways, or that we apply a little more force on the right ankle. And to figure out which control action will work the best, we can use our prediction from earlier to estimate how a particular control action will influence the balance of our exoskeleton. If we try enough of these control actions, we may just find the one that works. And that's precisely why we use model predictive control to balance. We can simulate multiple exoskeletons next to each other and simply choose the one that balances best. And that also brings us to the point why balancing is so difficult for robots like these. The more exoskeletons that we can simulate at the same time, the more control actions that we get to choose from. But at some point, we are running so many simulations that we've completely exhausted the computing power that our exoskeleton has available. It is therefore that we are proud to announce that the exoskeleton of Project March 10 will be powered by a graphics accelerated chip, which is capable of running a huge number of these simulations. This way, we'll definitely be able to run enough simulations to let us find that one control action that we need to keep our exoskeleton in balance.
Earlier, we discussed how the active ankle inversion-eversion mechanism helps with balance in a standing position. However, this joint does more than support balance. It also plays a significant role during walking. Over the past few years, we've learned how demanding training sessions can be for our pilot. The pilot needs a full focus. Each step requires the pilot to shift their body weight onto the standing leg before being able to lift up the other. Previously, this weight shift relied heavily on the pilot's upper body strength, pushing off with crutches each step. This process is exhausting, especially when you consider the exoskeleton adds an extra 40 kilograms that also needs to shift. With the improved ankle joint, the active ankle inversion-eversion mechanism helps with balance. The required effort from the pilot is reduced, and this makes each step less taxing, enabling the pilot to walk more comfortably and efficiently, which is also very beneficial for the ultimate goal to use the exoskeleton in daily life.
Let's think about this ultimate goal for a moment. What's the main purpose of an exoskeleton? Well, we believe that an exoskeleton should help the pilot stand up and walk in such a way that it requires little to no additional effort from the pilot. The exoskeleton does the heavy lifting, not the pilot. And with the added linears, we've gained full control over both our ankles, which will allow our pilot to weight shift much more easily, as well as to maintain balance through the model predictive control algorithm that we talked about. And with the added torque sensors, we'll be able to measure forces across all the joints in our exoskeleton. And these two things will allow us to start designing a walking pattern that will significantly reduce the added effort that's required from our pilot.
There's still one important change that we're making this year. As you've heard, we envision our exoskeleton being used in a dynamic concert setting, where people move around freely, enjoy the music, with a drink in their hand. The covers of the exoskeleton have always provided protection, just like our skin provides protection, shielding both the pilot and the internal components. This year, we specifically focused on making all the covers of the exoskeleton splash-proof. In our rotational joint, for example, we will integrate a flexible material that moves seamlessly with the joint while also sealing it from external liquids. Now, we can ensure Dan can fully enjoy a live concert without worrying about losing his balance, getting tired, or spilling his drink.
We've taken you through many of the key software and mechanical innovations that we're making this year. But how do we bring these systems to life? And to tell you all about that, we'd like to invite Stijn to the stage.
Thank you, Anneloes and Rens, for guiding us through the main software and mechanical innovations of this year. But how do we connect these two worlds? How do we ensure that the innovations from the software department translate into precise movements of the joints built by the mechanical department? That's where the embedded systems and electrical department comes in. My name is Stijn van Disseldorp, and I'm the lead embedded systems and electrical of Project March 10, or as we like to call it for short, the Embectrical department. The Embectrical department bridges the gap between the software and mechanical worlds. We ensure that the software running on a computer doesn't just stay in the digital world, but actually drives the motors and brings our exoskeleton to life. And there are two main challenges that the empirical department faces when bridging the gap, actuating our exoskeleton, and gathering sensor data about the exo itself and its surroundings. But let's start with actuating our exoskeleton. To move our exoskeleton, we start with our most important team member, our pilot, Daan. Through our own custom-made input device, Daan can intuitively select what he wants the exoskeleton to do. This input device, which can be placed on the crutches, consists of multiple buttons, which allows Daan to choose between different movements of the exoskeleton, like walking forward with varying speeds, walking sideways, of overcoming a level difference, sitting down, and standing up. With just the press of a button, Daan's intentions are registered. He gets confirmation of his choice with visual and haptic feedback from the controller. This input command is then sent to the main computer, which can be seen as the brains of our exoskeleton. This is where all the sensor data is gathered and the main software runs. Like Rens already mentioned, this year we've upgraded the computer significantly, allowing us to perform all necessary calculations with high speed in real time, so we're able to react quickly against external disturbances. But now, to actually move our exoskeleton, the computer sends precise motor commands to our custom-made motor controllers, the M-drives. The M-drives actually drive the motors and assures that these joints move exactly as the computer intended. Now, the speed and complexity required for our balancing goal not only ask more from our computer, but also from our M-drives. And that's why we have upgraded to a larger and more powerful microcontroller chip on these M-drives. But besides actuating and driving the motors, the M-drive has another big function. But we'll get to that one later. So now, I've mentioned actuating the exoskeleton. Let us now talk about the second challenge that the empirical department faces when bridging the gap between the software and mechanical worlds, gathering sensor data. To make sure our exoskeleton is aware of its position and orientation and its surroundings, our exoskeleton is equipped with a total of 40 sensors, 20 encoders that determine the angle that the joints make, 4 torque sensors, and 6 load cells that determine the exerted force of the motors, 2 cameras to detect level differences, and the final 8 are positioned in the feet, in the pressure soles. And this year marks the return of the pressure soles, because they are essential for our balancing goal. This year, we've completely redesigned the pressure soles, and we're now making use of 4 load cells per foot. Each load cell can be seen as its own force sensor, used to determine the exerted force of our exoskeleton on the ground. And because we are using 4 load cells per foot, we can precisely determine the so-called center of pressure. The center of pressure can be seen as an average of all these forces on the ground, or a balancing point. Like, imagine standing still. The center of pressure is right beneath you, between your feet. But the moment you shift your weight from one foot to the other, the center of pressure moves accordingly. Determining the center of pressure is crucial for our balancing goal. By feeding this real-time data into the model predictive control algorithm, we can precisely determine when the exoskeleton is about to lose balance, and then we can act accordingly to remain stable and remain in balance. To use the new pressure soles, we're introducing a new board. This board is located in the sole of the feet and gathers the information from the 4 load cells and sends it to the M-drive. And here we come to the second function of the M-drive, gathering sensor data from external sensors. This sensor data from encoders, force and torque sensors, and the new pressure soles is gathered, processed, and then sent to the main computer. In addition, this year we're introducing a new sensor, a sensor on the M drive, an inertial measurement unit, or IMU for short. An IMU measures its rotation and acceleration in 3 different dimensions. And because these IMUs are positioned on every M drive, and the M drives itself are positioned all throughout the exoskeleton, we can precisely determine the rotation and acceleration of 5 different crucial segments of our exoskeleton, 2 in each leg and 1 in the backpack. This means that we actually have a total of 45 sensors in our exoskeleton this year. So now, I've mentioned the 2 main challenges that the empirical department faces when bridging the gap between the software and mechanical worlds, actuating the exoskeleton and gathering sensor data. But there's actually a 3rd, underlying challenge that the empirical department faces: providing everything with power. Positioned in the backpack, there's a battery consisting of 15 cells which powers the entire exoskeleton. And this year, we're using a new type of battery, which increases its capacity by more than 20%. So now, our exoskeleton can walk for even longer. Another crucial part is providing everything with just the right amount of power. Because too much power and you'll fry your electronics. Too little and they just don't turn on. And that's why we've got the power distribution board. This board, positioned in the backpack, regulates the power coming from the battery and supplies everything with just the right amount. So the computer and all the M drives can all work as intended. And with that, I've come to the end of our technical overview of our exoskeleton. I've mentioned all the challenges that the empirical department faces. So let me give you a quick recap of everything that we've mentioned. First, the mechanical department introduced the coupled linears in the ankle, allowing for active stabilization against disturbances. Second, the software department introduced model predictive control, enabling our exoskeleton to predict movements and react quickly to remain in balance. And finally, the empirical department introduced redesigned pressure soles and an all-new sensor on the M drive. With all these innovations, Project March is pushing exoskeleton technology forward, one step at a time. Thanks to these advancements, the exoskeleton of Project March 10 will be able to decrease physical effort, stand self-balanced, and resist external disturbances by the end of July 2025. This is the exoskeleton of Project March 10.
At the beginning of this presentation, I asked you to imagine the electrifying moment of standing in a concert crowd, feeling the music, the energy, and the connection. For most of us, this is an experience we take for granted. But for millions of people with paraplegia, it remains out of reach. With Project March 10, we strive to change that. We believe mobility is more than just movement. It's about participation, independence, and the freedom to fully experience life's moments. Whether it's navigating daily life or standing shoulder to shoulder with friends at a concert, our goal is to give people with paraplegia that choice. In this design presentation, we showcase some of the innovations we are going to make this year. Combining these changes and building an exoskeleton from scratch is an immense task that we take up every year. But it wouldn't be possible without the support of our partners. You make sure that we, as Project March, can continue our vision of improving exoskeleton technology. I would like to take a moment to thank all of you for your support, whether it's through funding, components, or consultancy. Furthermore, we are lucky to receive incredible support from our community of former March members. I would like to thank all of you for being so invested in our project and for guiding us through the many challenges of this year. I would also like to give a big thanks to our family and friends. We know you may not see or speak to us as much as you did before this year, but we are very grateful for your loyal support. And now, there's one final group of people that should definitely be thanked tonight. A group of people that started this journey together and have worked tirelessly to bring the project to life. It is with great pride that I present to you the incredible minds behind our project. Here are all the team members of Project March 10. The software department with Karel, Casper, Rens, Milou, Haaien, Rames, Matthé en Max. The mechanical department with Anneloes, Tom, Sjark, Kira, Meerte, Nienke en Anna. Practical department with Stijn, Valentijn, Raymond en Thomas. The operations department with Siobhan, Martijn, Roos en Marieke. The management department with Cindy, Luca en Kirsten. And our 28th and most important team member, Dan. For a drink and a chat downstairs in the restaurant. Thank you all for coming to our design presentation.